video we are discussing about the electronic configuration of elements and how is it changing in a period and in a group, and we are discussing about different blocks, that is S, P, D and F blocks, discussing the electronic configuration in each block. And there are mainly three types of elements. They are metals, non-metals and metalloids. We are discussing these things in detail. If we are saying about the electronic configuration, an electron in an atom is characterized by four set of quantum numbers. Each electron of an atom can be characterized by four set of quantum numbers. They are principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. As already discussed, we know about all these four quantum numbers in the previous video. So please refer that if you haven't watched that one. So here principal quantum number denoted by N defines the main energy level, that is known as shell. That means if you know the value of N, we can understand the electron is in which energy level. And filling of electrons in subshells or orbitals of an atom is called its electronic configuration. If we are considering the electronic configuration and its change in the period, we can say that the number of elements in each period is twice the number of atomic orbitals available in the energy level. If we are considering the first period, there is only one subshell, that is S, and the S subshell can accommodate only 2 electrons. So, in the case of the first period, we know that the 1s1, that is the hydrogen, and 1s2, that is helium. The K shell gets completed and there are 2 elements and only one orbital. That is only S orbital, and there are 2 electrons present and 2 elements are present in the first period. Next one is in the case of second period. There are mainly 2 subshells, they are S and P. S can accommodate 2 electrons and P can accommodate 6 electrons. And there will be 8 electrons or the 8 elements are present in the second period. That means there are 3 orbitals of P and 1 orbital of S. Total 4 orbitals from S and P. And there will be 8 elements or 8 electrons can be present in that period. Similar pattern is followed in the case of the third period. And there will be 8 elements and 4 orbitals. And in the case of fourth and fifth period, there is a small difference. There will be 3d orbital, that is the transition metals present in the fourth period. So the total number of orbitals present is from S only 1 orbital, from D there will be 5 orbital, and from P there will be 3 orbital. So total there will be 1 plus 5 plus 3. That is 9 orbitals will be present, and the number of electrons accommodated is equal to 9 into 2, 18. That indicates that there will be 18 elements in the fourth period. Similar thing happens in the case of fifth period also. 5s, 4d and 5p orbitals, 5p subshells are present, which indicates that 1 orbital from S, 5 from D and 3 from P, total 9, and total number of electrons is equal to 18. And so number of elements present is also 18. And in the case of sixth period, there is a small difference again. There another set also comes, that is F shell, F block, which indicates inner transition elements. And in the case of sixth period, the number of orbitals will be 1 from S, 7 from F, 5 from D and 3 from P. Total there will be 16 orbitals, and the number of electrons accommodated is equal to 32. That is, total number of elements present in the sixth period is 32. And in the case of seventh period, similar thing happens here also. 7s, 5f, 6d and 7p. Total 16 orbitals, and number of electrons accommodated is equal to 32. That is, total number of elements is equal to 32. Next is the specialities when the elements are in the same group. That is the group-wise electronic configuration. Elements in the same group have similar valence shell electronic configuration. For example, in the case of S subshell, we can say that NS1 is a configuration. And if in the case of sodium, that will be 3s1. In the case of potassium, that will be 4s1. That is a similar valence shell electronic configuration is present. Only the number of group only changes. And elements in a group exhibit similar chemical behavior. If one of the element is reactive, the other element in the same group will also be reactive in most cases. We determine the block considering the orbital in which valence electron being filled. if the valence electron or the outer electron get filled in the p orbital, which indicates that it is a p subshell, that is in the p block. And next, if the electron enters into the f subshell, thus we can say that the element is in the f block. But there are some exceptions in this case. That is in the case of helium, thus we can say that the electronic configuration is 1s2, which indicates that it must have been in S block. But it actually belongs to P block. Why? Because in the case of helium, it has fully filled electronic configuration. So it is placed along with the noble gas in the right side of the periodic table. And in the case of hydrogen, thus we know that is 1s1. It should have placed along with the first group elements, that is alkali metal elements. But hydrogen is placed separately above in the periodic table. What is the reason? That is, hydrogen is actually quite different from the others. Because in the case of hydrogen, if it attains one electron, it actually gets the noble gas configuration. So it could have placed in the 17th group as well as in the case of first group. So because of this reason, it is actually placed neither in both groups and placed above in the left corner of the periodic table. Is the specialities of S block elements. They are reactive metals with low ionization enthalpy. That means ionization enthalpy is the amount of energy required to remove the most loosely bound electron from an isolated neutral gaseous atom. So, the metal in the case of S block elements, the outer electronic configuration is S1. So, it can remove its outermost electron and form noble gas configuration. That means they are reactive metals with low ionization enthalpies. They can easily remove an electron. They lose the outermost electron readily. And the metallic character and reactivity increases down the group. That means as we move from top to down of the group, the metallic character increases as well as its reactivity also increases. The reactivity of potassium is greater than that of sodium. In same way, it increases as we go down the group. They are highly reactive and never found pure in nature. They are actually highly reactive and they can only stay in the combined state and can never found in nature. That means in the case of sodium, we know that sodium hydroxide is present. In the case of potassium, potassium hydroxide, sodium carbonate, these all are present. But it is very difficult to see an alkali metal or S block elements in pure nature. Except lithium and beryllium, all other compounds of S block elements are ionic in nature. In the case of lithium and beryllium, both of these forms mostly covalent compounds, and all other compounds of S block elements are ionic in nature. For example, sodium forms NaCl, etc., which are actually ionic compounds. In the case of potassium, KCl, that is also ionic. So similar ionic compounds are formed. And what about P block elements? They are known as representative elements. The P block elements and S block elements are together known as representative elements. And the configuration of the P block elements are from Ns2Np1 to Ns2Np6, which indicates that the Ns2Np1, that noble gases are actually very stable and they show very less reactivity. And others we can see are halogen and chalcogens. They are highly negative electron gain enthalpy. They have highly negative electron gain enthalpy, which indicates that halogens are 17th group elements and chalcogens are 16th group elements. They can attain 1 and 2 electrons respectively to form the stable octet configuration. So they have highly negative electron gain enthalpy. Here negative means energy gets released during this process. And next one is non-metallic character. The non-metallic character of elements increases from left to right and metallic character increases as we go down the group. That means as we go from left to right in a period, the metallic character of elements increases. And as we go from top to down, the metallic character increases. D block elements. The D block element is considered from group 3 to 12. That means from group 1 to 2, 1 and 2 is S block element or S block elements, and group 13 to 18 are P block elements. So group 3 to 12 are D block elements or transition elements. The general outer electronic configuration is n-1d 1 to 10 ns 0 to 2. That is, the last electron gets filled in the d orbital and it extends from d1 to 10. It may be 1, 2, 3, etc. to 10. And all the elements in the d block are metals. They form transition complexes, that is colored complexes, and exhibit variable valency and show paramagnetism. They can be used as catalyst. For example, iron can be used in the Haber process. And the exception is in the case of zinc, cadmium and mercury because they have fully filled d orbital. They have d10 configuration. So they are exceptions in the case of the even compared to other d block elements. F block elements includes lanthanides and actinides. The lanthanides means atomic number 57 to 71. And if we accept lanthanum, we can call it as lanthanoids, that is atomic number 58 to 71. And actinoids are from 90 to 103. So next actinides extends from 89 to 103. And to the next portion, that is outer electronic configuration of F block elements, that is n-2f 1 to 14, n-1d 0 to 1 and ns2. That means the last electron enters into the F subshell. And all the inner transition elements or F block elements are metals. The actinoids can be steric, but they are more complicated compared to lanthanoids because they have various oxidation states. And if we consider the element uranium, atomic number 92, after uranium, the elements are known as trans-uranium elements. We can classify elements into three. That is, they are metals, nonmetals and metalloids. Almost 78% of the all known elements are metals. They have high melting point and boiling point. They are very good conductors of heat and electricity. We know that they are very good conductors. For example, in the case of iron, we can say that iron is a very good conductor, copper, all these are very good conductors. And they are malleable, that it can be made into sheets. And they are ductile, they can be made into thin wires. And they are solids at room temperature. And in the case of nonmetals, for example, oxygen, nitrogen, etc., they have low melting point and boiling point. They are poor conductors of heat and electricity. And they are not malleable and they are not ductile. They are solids or gases at room temperature. And there is another category called metalloids. That is, it have characteristics both that of metals and nonmetals. That is in between. Silicon, germanium, antimony, etc. are examples of metalloids.